There's a simple rule in mathematics that seems harmless at first, but once you accept it, suddenly bizarre things happen. A line can be chopped into pieces that have no length. A sphere can be split and reassembled into two spheres exactly the same size as the original. And for over a century, entire branches of math have depended on this rule. It feels intuitive, yet it also creates paradoxes so wild they sound impossible. So the question is, can we really trust it? Everything begins with the problem of choice. Think about this. Pick a number. Easy, right? Maybe 17, maybe 42. But notice, that was your brain doing the choosing, not mathematics. Math doesn't allow you to just pick. Formulas always give the same answer. Computers face the same issue. They don't generate true randomness. They only simulate it using clever tricks, like using the current time. So in math, how do we choose anything at all? The only way is to follow a rule. For whole numbers, a rule could be always take the smallest one. That gives us 1. For prime numbers, the smallest is 2. Easy. But the real numbers, they go on forever in both directions, with fractions, decimals, irrationals like pi, square roots, and more. Try finding the smallest real number. You can't. Even after 1, there's 1.01, then 1.000001, then 1.00000001. It never ends. So how do you choose? The truth is, we can't. Not without help. That puzzle is what drove a 19th century mathematician, Georg Cantor, nearly to the breaking point. Cantor revolutionized how we think about infinity. Before him, most people believed infinity was just one big, endless thing. But Cantor showed there are actually sizes of infinity. He proved that whole numbers and fractions are the same size of infinity, because you can pair them up 1 to 1. But real numbers, he discovered they form a bigger infinity, an uncountable infinity. This was shocking. Something that never ends can actually be larger than another thing that also never ends. But Cantor didn't stop there. He believed even these uncountable sets, like the real numbers, could be put into a neat order, just like counting 1, 2, 3. He called this a well-ordering. Here's the catch. No one could prove it. Not even Cantor. He believed it must be true, partly because of his faith, but mathematically he had no solid ground. His peers tore into him, calling his work dangerous and even insane. The rejection broke him. Enter Ernst Zermelo. At a conference in 1904, another mathematician announced a supposed proof that Cantor's idea was wrong. In the audience sat Zermelo. He spotted a flaw almost immediately, and within weeks he published his own proof that every set can be well ordered. How did he do it? By introducing a brand new rule, the Axiom of Choice. It says this: if you have infinitely many sets, each with at least one element, then it's possible to pick one item from each set. It doesn't tell you how the choice is made. It just guarantees that such a choice exists. This one axiom sounds innocent, but it unlocks the ability to order even the real numbers. It doesn't give you a smallest number after 1, but it guarantees you can always pick a first number in some order. And that means, with the axiom of choice, any set can be well ordered, no matter how infinite. Mathematicians were stunned. Some accepted it, others hated it. Because this rule, while powerful, also leads to mind-bending results, like the Banach-Tarski paradox, where one ball can be split into pieces and reassembled into 2 identical balls. So what started as a simple question, how do you choose, became one of the most important debates in modern math. Cantor's vision and Zermelo's axiom reshaped how we understand infinity. And today, whether we're designing computer algorithms, exploring geometry, or even thinking about randomness in physics, The axiom of choice sits quietly at the foundation. It reminds us that sometimes, in math as in life, the ability to choose isn't about the method. It's about believing the choice exists at all.